Hi everyone and welcome to another chemistry video. What we're going to look at today is how we can use carbon-13 NMR to not just tell us how many carbon environments are in the molecule, but also to tell us something about what's bonded to those carbon atoms. You see, when you bombard your molecule with radio waves, how many electrons there are around that carbon nucleus will determine what frequency of radiation is required to make that spin flip. Now that's just the background. So if a carbon atom is only bonded to other carbons and hydrogens, then there's nothing that's pulling those electrons away from it because it's not bonded to anything electronegative. As soon as it's bonded to an electronegative atom, or if there's a double bond, or even worse, a double bond to an electronegative atom, those are groups that are sometimes called electron withdrawing groups. So they pull the electrons away from the carbon nucleus, what we call de-shielding it. So that can mean that it will flip at a higher frequency. Now that all sounds interesting. Let's have a look at some spectra and see what I'm talking about. Okay, so the first thing is to consider, if you have a carbon that is only bonded to other carbons and hydrogens in single bonds, then you will find it in the 0 to 50 ppm range in your spectrum. There's a bit of variation within that, but that's where you're going to see it. If you've got a carbon bonded to a more electronegative atom, such as oxygen, nitrogen, chlorine, then you will typically find it in the 50 to 100 parts per million range. If it's got a double bond to another carbon, so it's an alkene or sometimes in a benzene ring and things like that, then you will find those carbon atoms in the 100 to 150 ppm range. Now, just an important point to note there is if you have a carbon-carbon double bond, then typically that means you have two separate carbons that have a carbon-carbon double bond, obviously. And so that can give you two distinct peaks if those two carbons are in unique carbon environments. Finally, if you've got a carbon double bonded to an oxygen or potentially double bonded to a nitrogen, but you're not likely to see those, and then you typically find those peaks in the 150 to 200 parts per million range. Sometimes they can go a little higher, particularly in ketones, and aldehydes they can be over 200. Okay, so what do these spectra actually look like? Oh, hang on, before we get into what the spectra actually look like. This is a reference sheet which is included in our team drive, and there's a link to it off the lesson plans. It has more detail than you need to know, but it's worth getting familiar with this. Anyhow, I'm not going to get into that in detail. I really want to look at some spectra. So here we have two molecules which are very, very similar in a lot of respects. We've both got three carbons, they're both symmetrical, they've both got an oxygen on the second carbon. The only difference is that the oxygen in the top molecule, propane-2-ol, is a single bonded oxygen in a hydroxyl group. And in the bottom molecule, propanone, what you have is a carbonyl group. So when we look at the spectra of these two, we see quite different spectra. There are some similarities, however. Both molecules have two CH3 groups, which are exactly the same. So they're both positioned in that range of, well, certainly in the 0 to 50 range, and typically because they are CH3 groups, they are found more down around the 20 ppm range. The bottom molecule, because those carbons with the CH3 are attached to a carbon with a double bonded oxygen, so they're quite close to that electron withdrawing group, they're actually slightly more de-shielded, so they have what we call a slightly more downfield shift. So their peak is around about 30 parts per million. So you can see that there. Both of those are your CH3 groups, the peaks that relate to that. In the top molecule, propane-2-ol, you have the middle carbon is a single bonded to an oxygen, and so you see that peak at around about 65 parts per million, while the second one is a carbonyl group, and you see that at around about between 205 and 210 parts per million. Sometimes you need to guesstimate off the graph. So simply looking at those two spectra will allow you to distinguish between those two compounds. Now, I always get asked, does how tall the peak is tell me something about how many carbons there are? And my answer to that is yes and no. If you're looking purely at CH3s and CH2s, then yes, usually a taller peak will reflect more carbons. But you can't really compare, say, a CH3 peak with a carbon double bonded oxygen peak, a carbonyl peak, because there's a lot of other factors that feed into it, the peak height as well. So yes and no to that question. Okay, so here's a couple of examples. We have two isomers of C5H12. So the structures you can see up on the top, you've got pentane and you've got 2-methyl-butane. Now, in this case, all you're going to look at is the number of carbon environments that are present because the functional groups in them are exactly the same. So the one on the left, pentane, has 3 carbon environments. The one on the right, 2-methyl-butane, has 4 carbon environments. Therefore, the spectra on the left is pentane spectra, and spectra on the right is 2-methyl-butane's spectra. Now, because both of these are just alkanes, all of their peaks are located in that 0 to 50 ppm range, and most of them are lower than that. You will see in the left-hand spectra there are the 2 taller peaks, which are the one on the far right relates to the CH3 group, the next one relates to the 2 CH2 groups. Similarly, in the spectra on the right, in this case you've got 2 different CH3 environments. So the smaller peak to the far right at about 10 ppm is the one that they've identified as carbon 4. The next one, the double height peak, is the 2 CH3 groups that are identified as carbon 3. So you can see there is some correlation there, at least for alkanes, between peak height and the number of carbons being represented. But it only works for alkanes or the alkyl groups. Okay, so let's look at some slightly more complicated ones. These are 3 isomers of C6H12. So you have heptene or hept1ene, 2,3-dimethyl-but2-ene, and cyclohexane. So the first thing to note is that 2 of those molecules have carbon-carbon double bonds in them, so you would expect to see peaks in the 100 to 150 part per million range. The other one is a straight alkane, so you would not expect to see any peaks up there. And so that makes it very easy to say, well, spectrum number 2 must be the cyclohexane because it doesn't show any evidence of a carbon-carbon double bond, whereas the other 2 do. The next thing you can look at is the number of carbon environments, and the 2,3-dimethyl-but2-ene compound, that's the one structure shown in the middle. You can perhaps see that that molecule is really symmetrical, so that actually only has 2 carbon environments. The CH3s are all identical, and the 2 carbons and the double bond are identical. So that only has 2 carbon environments, so that would be the first spectra on the left-hand side, which means the other one has 6 carbon environments and is the one with 6 peaks. Now, the hex1ene, you'll notice that the 2 carbons that are on the double bond are in different carbon environments. One's got 2 hydrogens on there and one's got 1 hydrogen on there, which is why we have 2 peaks, one at about 112 parts per million and one at about 140 parts per million. Okay, so when you're justifying which spectra you think belongs to which compound, you need to talk about the number of peaks in the spectra versus the number of carbon environments in the molecule. So spectra A must be compound X because compound X has X number of carbon environments and there are the same number of peaks in the spectra. And you also need to talk about the chemical shifts. You need to be quite specific. So the spectra has a peak at 10 parts per million, always use units, and this would represent a CH3 group, which you can see in the molecule, or whatever words you want to use, and I'll spend more time on that later. Okay, so here's another example. Here we have 3 spectra which relate to isomers of C4H8O. And in this case, the 3 isomers are butanone, butanal, and 2-methylpropanal, so 2 aldehydes and a ketone. You could also, with that same formula, have something with an alcohol and a alkene in the same molecule, and you will see ones where we have combined spectra, or combined functional groups, I should say. So in this case, obviously the branch chain molecule methylpropanal only has 3 carbon environments, so that's the bottom spectra. But the 2 spectra at the top are much harder to differentiate. Okay, both relate to butanone and butanal. So they're both 4 carbons, they're both straight chain, they both have 4 carbon environments, they both have a carbon-oxygen double bond. So how do you tell them apart? Well, to tell them apart, you really need to look at the spectra. And I'm just going to show you those spectra, the structures, I should say, and I'll show you those in a second. Okay, so if you have a quick look at this image, you'll see 117 here, which is butanal, and 118, which is butanone. And what you will see is that in the butanal, you have your carbonyl group, and then you have 1 carbon immediately adjacent to the carbonyl group, the next one further away, and the next one further away from that. In the butanone, you have 2 carbons that are adjacent to the carbonyl group, and 1 carbon that is further away. Now that will have an impact because the closer, or the carbons that are immediately adjacent to the carbonyl group tend to shift somewhat further downfield. The further away you get from the carbonyl group, the closer those CH2 and CH3 peaks get back to the original. If we have a look at these 2 spectra at the top, you'll see that the one on the left has 2 peaks around about 30 to 40 parts per million, whereas the one on the right only has 1 peak around that and has 2 peaks between 10 and 20 parts per million. So from that, I would think that the spectra on the left is butanone because you've got those 2 carbons that are immediately adjacent to the carbonyl group, whereas the other one is butanal because you only have 1 carbon that is immediately adjacent to that carbonyl group and 2 which are further away. And of course the last one is the methylpropanal. Okay, so I hope this has given you all a bit of an idea about how we might use NMR to identify both what type of functional group we've got present in a molecule and how many carbon atoms. Without additional information, you can't make any definitive answers about the structure of a molecule, but this provides a really good starting point. In the next video, I'm going to talk about infrared spectroscopy and how that can support NMR to determining more about the structure of a molecule. Okay, I'll see you then.